the next presentation will be by Dr. Giovanni Vorraro, who is a research scientist at KAUST, working with Professor Turner. And we'll talk also about carbon-free engines. So when you're ready, you can start.
Yeah, thanks so much for the introduction, Professor Diana. So, as Professor said, I work with Professor Jamie Turner. Thank you, Jamie, for your nice presentation to this valuable audience to excite these people. That makes my job a little bit more difficult. I'll try to keep up with him. So, my name is Giovanni. Today, I'm presenting application of carbon-free fuels to non-conventional internal combustion engine. Jamie gave a really nice overview, insightful overview about the activities that we are doing, a nice helicopter view of the things that we are doing at KAUST, our vision in terms of fuel and engines. I'm going to talk specifically about some particular engine that maybe are not really well known, for sure, not conventional one. I'm going to give you a short introduction of myself. Then I'm going to give you an introduction how we want to use carbon-free fuels in non-conventional internal combustion engine. Specifically, application for Wankel rotary engine and opposite piston two-stroke engine, that maybe you heard about them. Then we are drawing some conclusions. Short introduction of myself. Again, my name is Giovanni Vorraro. I started my PhD at the University of Naples in 2011. I'm an engine enthusiast, as Jamie is. I chose mechanical engineering because of engines, practically. I made my PhD on turbochargers, automotive turbocharger. We had a small lab that we could test automotive turbocharger. At that point, that was really interesting to test turbocharger in terms of surge, choke, and defining the performance of turbocharger under pulsating condition. That was the hot topic at that point, and I made my PhD on that. Also had a side project on electric bike. We were already speaking about electric stuff at that point. And I was the PI on that project. It was like financed by the Minister of Instruction in Italy. Then I moved to CERN because I want to make my curriculum more international. I was not really good with English language at that point, so it was a right move for me to make my curriculum more international. At that point, I was the only mechanical engineer in the electronics section at CERN, particle accelerator for people that are not aware of them. And I was doing some study on heat transfer while applying measurement system using real-time and FPGA systems, so about controlling stuff. Then I was kind of fed up with particles, and I want to be back on the engine side of the world. So I went to the research, as a research fellow to the LOCARTIC, that was a research center in Malaysia and Singapore, in cooperation with Imperial College, back on the transfer and performance evaluation of turbochargers. Finally, I got the position at the University of Bath, where I met Jamie, actually, starting a research associate, made a different step of career there, up to the assistant professorship. And back again on engine, this time new architecture applied to intelligent powertrain for hybrid application. Finally, I joined KAUST in 2011. With Jamie set up many objectives. For sure, like one of them was like to make research on innovative, okay? Yeah. Make some research on innovative architecture for engine applied to hybrid powertrain, and again, rotary opposite piston. We were looking, of course, like we are looking for innovative fuels, ammonia, methanol, ethanol, stuff like that, applied to internal combustion engine. And of course, like we are also carrying out some research regarding the optimization of hybrid vehicle layout, because we are really interested in the hybrid technology more than the BEV itself. So we are implementing many numerical models in the simulation software in order to optimize like size of battery or size of the engine and try to find a good strategy in order to minimize the consumption and increase the efficiency of the overall vehicle. Finally, of course, we are doing research on hydrogen internal combustion engine, something that I'm going to talk right today. And of course, we are interested in fuel cell in applications still applied to the automotive world. This was like a bit of my short introduction. Today, I'm going to speak about using carbon-free fuels in non-conventional internal combustion engine, specifically in Wankel rotary engine and opposite piston engine. Why we are doing this? Like in our research, we want to push forward the concept that goes towards the optimization and synergistic operation between engines and fuel. We know that fuels and engine are not perfect, but they may be perfect one for each other. A bit like human relationships, you know, like they can help one each other. And of course, like there are some examples that I'm going to give you today, where like the fuel can help the engine in enhancing their performance, or in the opposite way, the engine is very suited for the fuel that we are considering. Today I'm talking mostly about hydrogen, and as I was saying about Wankel and the opposite piston engine. So we believe that hydrogen is really suitable for Wankel engine because one of the drawbacks of the Wankel engine is like it has a very slow combustion when it is with gasoline. Given the disruptive combustion of hydrogen, it can balance this drawback, so can be really used and be beneficial for Wankel rotary engine. On the opposite side, we believe that the opposite piston two-stroke engine is really suitable for the hydrogen fuel. It can help like the disruptive combustion of hydrogen because like the opposite two-stroke piston engine has a really nice surface to volume ratio atop that sand that can help the hydrogen in reducing the heat loss when the combustion is disruptive, so when temperatures are very high. So that's why we believe that we can do the research in this way, and we can go towards this kind of optimization and synergistic way to operate between fuels and the engine itself. Let's start with the Wankel rotary engine. How many of you are from the engine world? I know that there are many mechanical engineering engine world guys. Have you ever heard about Wankel rotary engines? Can you raise your hand? Not many of you, as expected, okay. So not bad. I'm reporting here an example of Wankel rotary engine. This one is the famous Mazda 13B Renesis engine. Of course, like Wankel rotary engine are totally different from reciprocating piston engine. Instead of having piston, core rod, and crankshaft, they have like this kind of rotor that is triangular shaped, that is rotating inside this chamber that has a shape of kind of a bean. And rotating is creates the displacement, and also like all the phases of the classic internal combustion cycle: compression, ignition, expansion, and exhaust. Here you can see like the classic inlet system and exhaust system that is pretty similar to internal reciprocating combustion engine. This engine is a side-ported Wankel engine. Here you can see the transfer port, the inlet one and the exhaust one. The rotor is rotating this way, as you can see, as you can imagine, and the displacement is increasing and then decreasing up to the top dead center, that is this point, where you can find the two spark plugs in this case that are igniting the mixture of air and fuel. Then the fuel is the gas are expanding this way, rotating, and then they're going to be exhausted in the exhaust system. This is again like the Mazda 13B Renesis engine. If you are really fancy of hearing a really nice engine sound, I suggest you to go on YouTube and look for the Mazda 787B racing car. That was one of the most powerful Le Mans car that was also banned because it was too powerful compared to the classic four-stroke engine. And the sound is really amazing. So if you are really fancy, you can do this kind of research. On the left side, you can see the AIE, that stands for Advanced Innovative Engineering 225 CS engine. 225 is the displacement of the engine, 225 cubic centimeter. In this configuration, we have also an external expander that is an additional device that we were testing. I'm saying we were testing because this was the engine of the project that when I joined the University of Bath with Jamie. The aim of the project was to test the engine and apply the engine to an intelligent powertrain able to provide the right power to an hybrid layout for a vehicle, of course. We tested this engine specifically, and let's go to the performance of this engine. Again, there are not a lot of you from the engine world, so I'm going to be more specific regarding this. Many of you, I believe, that know that this is like a kind of classic pressure cycle that happens inside the chamber of the engine. We have the classic compression phase, then addition of heat at isochoric addition of heat at constant value, then expansion, and there is the spontaneous exhaust phase right here, as you can see. Now, from people that are kind of used to this kind of cycle, they can easily recognize that this is a cycle, but it's not the best one that you can have in internal combustion engine. Usually in a classic four-stroke, latest technology, you can have a maximum pressure of around 50, 70, 80 bars. That means like you are collecting more work on the crankshaft, the engine is more efficient, is using more efficiently the fuel that you are injecting inside the engine practically. So here are already evident the drawback that I was talking about to Wankel engine, that is very slow combustion. If you translate this diagram that I reported for the speed of 4,500 RPM and 3 different brake mean effective pressure, that is like the translation of the power, in the log-log diagram, you can easily say what I was saying, like the combustion phase here, especially for the lowest power, is very slow, given by this like rounded shape on top. Like the addition of it is not instantaneous as we want from the ideal cycle that is applied to this engine. So the combustion is very slow. That means like this relate is very slow, not very efficient, lot of emission, not very again, not very efficient in terms of mechanical efficiency. So we want to avoid just these kind of things. Indeed, like we made a heat release analysis on the pressure cycle. You can like estimate which is the rated RRZ versus the crankshaft position. And as you can see, like the starting of the ignition is around 522 degrees of the crankshaft, but the entire release of it is taking something like 140 degrees of the crankshaft. That is, for an engine, is forever. Classic four-stroke engine can do this kind of job in 50 degrees. That means are much faster, so you can release the heat in a very efficient way at very, let's say, constant volume, and then you are having a nice efficiency. It is not true for the Wankel engine. Also, the rate of heat release is very slow. As you can see, we have a peak of 9 joule per degree at highest BMEP, while at the lowest is just slightly over 4. That is very, very low. Again, for four-stroke engine, you can have value around 50 or 70 joule, or even more, 100 joule for high performance four-stroke engine. So that's why we believe that hydrogen is really suitable for Wankel rotary engine, because the disruptive combustion of hydrogen inside the rotary engine can improve a lot this kind of behavior of the engine itself. We will see why this happens. So again, we believe that there are many advantages of using hydrogen in Wankel engine. For sure, like the poor combustion chamber shape is mitigated by the hydrogen short quenching distance. Jamie was already talking about this. The hydrogen is really able to go fast inside the chamber and like quench at a very short distance. Also, like differently from four-stroke engine, the combustion chamber in a Wankel rotary engine is rotating with rotor, so it's a moving combustion chamber. So you will have some pockets that are unburned, some pockets that start the burning process. Hydrogen is very suitable for this because like the egg flame speed can reach all over the chamber in very low time, of course. And of course, like when you are injecting hydrogen in this kind of engine, you are also solving out the problem of unburned hydrocarbons when you have the overlap of the inlet and exhaust system, because actually you are not injecting any carbon molecules, so you won't find any unburned hydrocarbon at the exit. You will find at least, at the very best, just hydrogen. And of course, like Wankel rotary engine not having high pressure and high temperature, it doesn't have also like a lot of hot spots that reduce the pre-ignition problems that are really important when you're applying hydrogen to internal combustion engine. Finally, the long period of intake that it takes more than it is not the classic 180 degrees, it's slightly more because the Wankel rotary engine operates over 1,800 degrees, 3 crankshaft revolution to complete one cycle. Makes us like we can apply also low pressure direct injector. As you can see on the application on the side, here is reported the Mercedes-Benz C111 engine from the past that is applying, of course, like direct injection, low pressure injector for Wankel rotary engine. That is again another advantage of this engine. Of course, this engine doesn't have only advantages. There are also some disadvantages. And of course, like there are the top land that I'm going to show you in a bit that can cause like pre-ignition problems. That can be some hot spots in the top land of the rotor because like it has its own volume, and so the gases can be trapped there that can make this a problem. And of course, like as I was saying before also, Heat losses can be very high because of the shape of the chamber. It's an elongated chamber, combustion chamber, that is not ideal for combustion. So we want to avoid this kind of two disadvantages. Here I'm reporting for you an example of an air-cooled rotor with this sealing grid. This is like the top land that I was talking about is this area. As you can see, there are a lot of crises where it can be like Zuno hotspot because it's very difficult to cool down that area. That can be like problems for pre-ignition in hydrogen. Here you can see the side sealing system. You can see like the internal gear with the ball bearings of the rotor, and of course, like you can see also like the apex seal that are used to seal the chamber, the three chambers that are rotating. Here on the right side, there's an example of the combustion chamber. The combustion chamber specifically is this one at EDC, like this side and this other side. You can see the two spark plugs. And there is the recess that makes like possible to transfer the fluid from like this side to this other side. So as you can see, the shape of the combustion chamber is not really optimal when you analyze it from a surface to volume, surface area to volume point of view. That's why the heat loss is very high in Wankel rotary engine. Of course, we are working on both these aspects when we are doing our job, especially during simulation. We don't have still an engine running, but we are going to have like in a few months some engine that are running here at KAUST. So it will be really interesting to see what we are predicting from the simulation, if it is really true in the real life. As you can see, like pore surface air to measure as I was showing before. We moved fast to simulation. I'm happy to say that these results are provided by Mr. Kevin Moreno Cabezas, that is in the audience with you. Please, Kevin, raise your hand so people can recognize you if later on want to ask you something. I'm really happy. Of course, Kevin is working Professor in CFD group. Most likely you know him. So, and we were analyzing in this study like 5 configuration in terms of injection timing for pure port fuel and Wankel rotary engine. The geometry is the same of the AI 225 CS. And of course, like unfortunately, I cannot report the results in clear because these are right now submitted for a paper. But at least I can give you like an overview of what's happening. We are, of course, like studying different injection timing. I'm not even reporting the time because it's still confidential. But you can see the difference between the different solution. Of course, like when you're starting earlier or later, the injection of fuel can be very beneficial or can be very worse, as you can see from the animation. For example, if you take in account this simulation, most of the fuel that you are injecting is going to be like forwarded to the exhaust. This is the inlet, this is the throttle valve, the injector on top. And as you can see, most of the fuel is just going through the exhaust, not even barbing maybe. There are some other configuration maybe like this that most of the fuel is trapped in. I'm showing here the air-fuel mixture ratio. As you can see, like the green, the red color is like the richer side, and the blue color is the leaner side. So you can appreciate that different injection timing in port fuel injection Wankel engine can make a lot of difference when you come to the final combustion. We made another study, this time studying the direct injection, no more port fuel injection. The geometry is still the same. The model setup is still the same, but this time we are injecting the fuel directly in the chamber, not port fueled. Even in this case, that can be like can be considered an ideal one. Even from a simulation point of view, there are some pros and cons. As you can see, we studied 4 different strategic positions of the injection. We made some study before, and we decided to apply the injector in 4 different places with 4 different characteristics. And as you can see, even just with the same injection characteristic, of course, injection timing, injection mass flow rate, and as you can see, just moving the injector from a side to another, it changed a lot the way that we are mixing the fuel and then we are doing the combustion later on. Mostly of the research has been done using the injector in this position. I can like discover it is like it is placed perpendicular to the major axis. And as you can see, it's not the optimal solution. We find there are many other solutions that are much better in terms of retaining the fuel inside the engine and then efficiently be burned later on during the combustion process. Namely, if I remember correct, this one is the best one, the last one. As you can see, a lot of fuel is retained inside the chamber and then can be combusted. Wankel rotary engine have another problem. There's another problem that are the pocket of the spark plug. As you can see, when you are injecting the fuel, this pocket, especially here, make the fuel pass from a chamber to another. You want to avoid this. That's why an optimization of the position injection times is really needed in order to have an high efficient engine later on. Again, these results are provided by Kevin. We are very, very happy with this preliminary simulation. We hope to confirm the results with the real engine later on installed in one of our lab at KAUST. Results again, from a pressure cycle point of view. Of course, we demonstrated like on the left side, you can see the results for the port fuel injection engine. We could demonstrate that just changing the injection timing, we can have like, again, the disruptive combustion in hydrogen that we were hoping for, like rising the pressure very high from 15 bar to up to 45 bar, or otherwise mitigate the effects with a kind of mild combustion later on. Just like, or otherwise even not having combustion at all if the configuration is very bad, like we are injecting and we are not combusting anything because we are losing all the fuel at the exhaust, something that we want to avoid, of course. On the other side, these are the results for the direct injection, kind of same behavior, but this time, like, of course, the meaning of the results are different. In this time, we are evaluating the position of the injector itself inside the chamber. So, and even in this case, we can choose to go from a disruptive combustion that rise up the pressure very fast or something that is very mild. So there are many scenarios in the middle. We are studying this with Kevin and Professor Ong group. So we hope to, we answered our main question that hydrogen is suitable for Wankel engine. Now we are in the process of optimize the combustion, and there is something that is very useful and very efficient later on. If you are interested in more detail, this time like with the values and stuff like that, you can go for this paper that is under submission, numerical analysis of hydrogen injection and mixing in Wankel rotary engine, that has been submitted to the SAENA, that is the SAE, Internal Combustion Engine Conference, happening in Capri next September. So it's going to be published by September, I hope. So you will have all the full overview with all the details of the data that I'm right now showing. Let's move to opposite piston two-stroke engine. How many of you heard about them? At least one, two? Yeah, okay. At least all the people from my group heard about them, likely. They are two-stroke engines. That means like they can make the cycle, they can conclude the cycle in just two-stroke of the engine. I'm reporting two-stroke of the piston. I'm reporting here different architecture of the two-stroke piston engine. We will have like, the Takeides power here. That is a classic one that is produced and researched on Takeides company that is in the USA. Then we have a Junkers Jumo 205. I personally made this picture at the Polish Aviation Museum last September. I was at conference, SAE conference, so I had the opportunity to go to the museum and take the picture. That means like this kind of engine are not really new concept. They were already used in the past for aviation application. And also like kind of some animation that can give you an overview of how this engine works. Of course, like as the definition says, there are opposite pistons that are going back and forth, compressing the fuel between them, then doing the combustion, expanding, and of course, like exhausting the gases later on. Differently from a four-stroke poppet valve engine, the transfer is made by using the transfer ports that are these little holes here in the cylinder, okay? The piston going up and down, cover and uncover these holes, so make possible to exhaust or inlet the fluid, relying on the pressure of the fuel itself. At the inlet, the pressure of the inlet fluid is higher than the one in the cylinder, so the fluid, fresh fluid goes in, then make the combustion, the pressure rise a lot, then when it opens again, like the pressure brings the fuel outside the engine. Of course, this kind of engine, most of them running on diesel fuel, so they are compression ignition engine. That's why usually they use direct injection that are, of course, like these other little holes that are placed at TDC, top dead center of the engine, when the two pistons are kind of kissing together, maximum compression time. You are injecting the fuel, it's auto-ignite, and then you have the burning process, the combustion process, okay? This is like the mechanism of how opposite piston engine works. Of course, like the shape of the piston are a bit different from conventional one because they have to include the space for the injection spray to be included between the two chambers. Even the chamber is like obtained on the top of the piston, as you can see, very similar to diesel engine. So this is like the operating mechanism of opposite two-stroke piston engine. Of course, we believe that, as I was saying at the beginning, that opposite piston engine two-stroke are very suitable for hydrogen as a fuel because, like, given that the hydrogen has a disruptive combustion and given that the engine itself has a good surface to volume ratio that reduces heat loss, it's a good match between engine and fuel. And of course, like, another advantage is that, like, two-stroke engine have to run very lean because of the scavenging loss. So that means that hydrogen is still very suitable because, like, as Jamie was saying before, the flammability of the fuel is very high, so you can go even up to lambda 10 and you still have a combustion inside the chamber. Another advantage is, like, you don't have, again, any carryover of unburdened emission because you are not injecting any carbon as a fuel, it's just pure hydrogen. The fuel mixing will be extremely rapid with injection at top dead center. So, and you can overcome the reduced time windows that you classically have in two-stroke engines. You can practice an HCCI type of combustion that, of course, like, give you the opportunity to mitigate the NOx production because, like, you can reduce the highest temperature of the combustion. And also, like, you can apply the variable compression, a variable compression system to this kind of engine that is, like, much easier than when it is applied to a four-stroke engine. I'm gonna show you right now something that is just related to that. Then for not popped valve engine, the elimination of exhaust valves mitigates the brake ignition. You know that big two-stroke engine, like the ship vessel engine, they have both transfer port and pop valve. When you don't have popped valve, you can just avoid the brake ignition problem because, like, you don't have the popped valve that usually are hot spot inside this kind of engine. While for the opposite piston engine, the architecture that I was showing before, the gaseous injection eliminates well wetting, enabling smaller engine frame size because when you're injecting gases, you don't have that the problem of well wetting, so you can reduce the size of the cylinder, and they have even better surface to volume ratio because, as we can see later on, reducing the bore to stroke ratio can increase, like, can improve the surface to volume ratio. Finally, still for the opposite piston engine, as I was saying, the good surface to volume ratio means less heat losses. That means, like, also higher efficiency for the engine itself. Some disadvantages also for the two-stroke. Two-stroke piston is already heavily thermally loaded. That means when you're applying hydrogen, it's even worse because, like, the disruptive combustion is going to increase rapidly the temperature in the piston. You don't have really a cooling system for piston in two-stroke engine, so this is going to be a problem. And also, like, you have to apply for sure direct injection because, of course, like, you don't want to lose any fuel in the scavenging processes. And this means, like, we have to develop a specific technology to inject, like, high or low pressure hydrogen directly inside the cylinder in a very complex geometry that can be like the one formed by the two pistons that are kissing together. So there are some other architecture of two-stroke or opposite piston two-stroke engine. One is this one that doesn't have the crankshaft rotating, but they have, like, applied two linear electric machines that are absorbing the power coming from the piston. In the middle, you still have the classic configuration of two pistons coming back and forth here. You can have inlet and exhaust. And then instead of having the crankshaft, you have just two linear electric machines. That is very suitable when you are talking about hybrid vehicle because you don't have anything that is rotating. You can, the shape is a bit odd in terms of engine. It's a very long engine, so, but at least you can recover the engine, the energy directly in electric form that can be, let's say, delivered to any battery or any electric motor inside the vehicles. One of the exemplar is the Liberty Intelligent 20 kilowatt electric energy. That is a company that is in the UK. We are working with them, actually. Most likely, we are going to have one of these engines here at KAUST. And Jamie itself developed a concept regarding an opposite piston engine using a linked X-cross between the piston. We have two cylinder, then we have 4 pistons that are going back and forth, and they are linked by this X-cross link. So when one piston is expanding, it's dragging the other one to compression and all the way around. So the name of this patent is Isotope X, and it was patented by Tunio Buff, but Jamie let me know that they managed to transfer the patent here at KAUST, and most likely we are going to do some research, even real research on something like this. If you are really curious about this, you can ask Jamie about more detail. He will be very, very happy to illustrate you what's going on this kind of prototype. So I was talking about the surface to volume ratio. Of course, like I already mentioned all the advantages, but we could find in our research that using the kinematic advantages of opposite piston engine, we could even improve the surface to volume ratio. Specifically, we were researching on the crankshaft phasing between the piston. Of course, like when the engine is working in the normal way, there is no offset between the crankshaft. Both the piston are TDC, both the piston are BDC. But you can introduce an offset in the crankshaft. So you can make the piston, for example, the intake piston that can be later than the exhaust. So you can change the way that the displacement is developing across the crankshaft. And in that way, like studying the kinematics, we could improve the surface to volume ratio. But the main aim was like also to adjust the compression ratio while the engine is running. And of course, like we studied different configuration of the engine with different crankshaft offset. What we saw is like that adding the, of course, like changing the compression ratio, introducing a crankshaft offset was also changing the swept volume of the engine, because like now the development of the displacement is not more symmetrical. And of course, we were also changing the port timing of the engine itself, that again is not more symmetrical like in classical application. Usually what we do and what we did in our research was like to use the exhaust piston, the exhaust that is uncovering the exhaust port, the piston that is uncovering the exhaust port to be ahead of the intake piston, or if you like, the intake piston is going to come later than the exhaust. Why that? Because like we want to uncover the inlet ports later than the exhaust ports in order to have more inlet phase when the exhaust ports are closed, so we can inject more fresh air and we have less scavenging problem later on. And in our study, we were using like the exhaust crankshaft as the reference system for the study. So when we are seeing the plot later on, we are referring to the exhaust crankshaft position as a reference. In the study that we carried out, we used the data from a general opposite piston engine. So I'm reporting here the data. The bore was 75 millimeters, while the stroke was 41 millimeters. So the bore to stroke ratio is nearly 2, pretty high. But the important things, if you are really interested in the data, you can find all the data in this essay paper that Jamie authored. The important thing is like the heights of the inlet and exhaust port are pretty similar. That means like they both, when there is no crankshaft offset, they both open and close at the same time. I'm going to show you the results right now. We made the study using a maximum compression ratio of 40:1. That is very not typical in this engine, but Jamie made some research on a particular engine that was going up to this compression ratio, so it was worth to us to study this kind of configuration. And then we introduced a crankshaft offset in the engine in order to achieve 25, 20, and 15:1 compression ratio while the engine was running. That are most usual compression ratio for compression ignition engines. Let's go straight to the results. This is like the normal configuration. There is no offset between the crankshaft. Both the pistons are moving the same way. They are kissing together at TDC. They are like a BDC together. So as you can see, everything is symmetrical. Here there is like the development of the displacement for the single cylinder. There are two lines here, the red and the blue. They are totally overlapped because everything is symmetrical. That's why you can just see the red one. And this is the total displacement that is, of course, like the sum of the two displacement of the piston that are moving. Even the port timing is symmetrical. As you can see, there is like the inlet and the exhaust port that are opening pretty much at the same time, and is symmetrical around TDC. And the most important, like we are having the maximum surface to volume ratio at TDC, something that we really want to avoid. It's not bad, like in terms of absolute value, but we want to avoid just these kind of things. We don't want the maximum surface to volume ratio at TDC, but we want to reduce it and move it somewhere else where the combustion phase is advanced and temperatures are lower, so we can avoid heat loss. For this configuration, the engine was able to do a displacement of 770 cc, of course with a 40:1 compression ratio, and like both the surface volume ratio and the max one are coincident. There are 5.21. That is not bad, but it's not even the best that you can achieve with this kind of engine. Then we applied the crankshaft offset inside the engine. So one piston is reaching TDC, the other one is a bit later, so they are not kissing together. As you can see, the results now are pretty different in terms of port timing and even in terms of surface to volume ratio development. Pretty much the displacement is the same, is varying not that much, like the maximum variation is just minus 2.4%. But what is important is like that in this case, in this case, like the exhaust phase is still the same because we were using it as a reference, but now the intake phase is coming later. That means when the exhaust port is closed here, you still have the intake port open. So you are still introducing fresh air in. So you are increasing the volumetric efficiency of the engine. That's why you can recover more. You can use like the fuel and the engine in a more efficient way. You are not losing any fuel at the exhaust. That's why you can employ hydrogen in a very easy way, given that you have the right injection technology. Again, there's the comparison between like the three compression ratio, 25, 20, and 15. And also like in terms of development of the surface to volume ratio, now we have that the maximum at TDC, the value is pretty lower than the one we were observing. Now we have something like 270, 215, and 169. And we also moved the max, the peak of the surface to volume ratio somewhere else from TDC, where the temperature should be much lower, so we can reduce the heat loss as well. So the takeaway of this study is that given a fixed maximum compression ratio, that in our case was 40, when you are introducing a crankshaft phasing, of course you are obtaining a better surface volume ratio. And of course, like the delays of the inlet phase improve like the volumetric efficiency of the engine, and then improving the overall efficiency of the engine. The only problem that in introducing this kind of phase, you are reducing slightly the swept volume, so the capacity of the engine is slightly lower. Also, reducing the maximum CR, like if you configure the engine having a maximum compression ratio of 30 instead of 40, you are having that at that new max compression ratio, the surface to volume ratio is better because like numerically the results are much better. But when you are introducing the crankshaft phase, the results that are coming later are pretty similar. So you are not changing a lot the surface to volume ratio later on when you are introducing the crankshaft phasing. Finally, with the fixed max compression ratio and swept volume, if you do a sensitivity analysis on the bore-to-stroke ratio, you will see that reducing the bore and increasing the stroke will also improve the surface to volume ratio. But this is like a classic results that you can find in the literature or even for four-stroke engine. It's not a novelty, it's something that we knew from the starting point. Some conclusion on my presentation. Hope you enjoyed it. So for sure, like what I want to illustrate, that new carbon fuels, carbon-free fuels can enable the advancement of non-conventional internal combustion engine architecture, as I was showing before, like something that can be considered the old, like the Wankel or even the opposite piston, can be like can be used again by using a new carbon-free fuel. And the research should be aimed just to maximize this synergy between these new fuels with this kind of non-conventional energy in order to, of course, maximize the energy conversion, and then the efficiency of the engine itself. Finally, we should do this kind of research because like current and new digital tools give us the opportunity to study in a better way this kind of solution. Most likely, many old unsuccessful solutions of the past, they were unsuccessful because they didn't have any tool to study properly this kind of things. Now we have the tools, we have mega computers, we have simulation tool, AI, machine learning, so we should do that in order to achieve these results. And finally, we really believe as a group that research on internal combustion engine shouldn't stop right now because like Jamie said that engine was a silver bullet. It is true when just the engine was around. Now that there are many technology like hybrid technology, battery electric technology, we cannot consider it anymore a silver bullet itself. So we have to take in account all the technology that we have in order to maximize like the efficiency of the transportation system. Of course, as Jamie was saying, some of the application cannot be pure electric because just the power and energy density or weight limitation of batteries are limiting these kind of things. You can think about ship, vessel, or aircraft. It's not really possible to have them pure electric. And of course, like there are many advantages of using this kind of new e-fuels in combustion, again, like energy and power density. And we have to take in account also that batteries are not clean as they want us to believe. Being an engine guy, politicians made me feel like a dinosaur, even if I'm just 39 years old. But I really hope and believe that we are going to be back stronger than ever. Thanks so much. I'm really enjoyed to give you this presentation. And if you have any question, I'm open to question. Here are my details if you want to follow up this discussion, but I'm open to question right now.
Thank you very much, Joe. Excellent talk.
Oh, thank you.
Question? Okay, I have a question, two questions actually. First, why is it more interesting to consider the opposite piston two-stroke engine compared to the just regular two-stroke engine?
Well, again, you have a better surface volume ratio. Like it has been demonstrated that a two-stroke opposite piston engine is able to reach an efficiency of 45% or higher. That like just this number itself gives you the explanation. Of course, there are some disadvantages like the shape factor of the engine itself that is long, and you are introducing more friction because of the system. But again, optimizing everything, and with the new technology, we are really aiming something that is 50% efficient. And of course, with hydrogen is much better because like you don't have any hydrocarbons at the exhaust, and that means like everything is pointing out that both the hydrogen and the opposite piston engine are really suitable one for each other. Of course, like even in we can see this kind of application mostly for heavy-duty application, mostly for hybrid application, not like connecting a drivetrain to the engine itself. And that's why, like, they are really highly efficient. Of course, there are many challenges in this, like the injection system is not an easy one, because you have to inject the fuel in a particular way when the pistons are kissing one each other. So you have to study really well the spray inside the chamber in order to have the right amount of turbulence, the right amount of... It's not really a problem for hydrogen, which it's, as Jamie was saying, is really angry to bar. But if you want to consider more classic application or diesel with like diesel engine that are already really high in efficient, you have to study all these parameters. That again is much more challenging and interesting than studying like just an electric vehicles.
Yes, we have a question from the audience on, you have a microphone behind you.
So it's a question that is a bit more general. It asks, does the quality of the material affect the form and the quality of energy wanted?
The quality of the material, sorry?
It's asking, I'm not sure I understand the question. It's exactly phrased this way. Does the quality of the material affect the form and the quality of the energy wanted?
Well, I believe that is referring to the Wankel engine. Maybe he wants to say the quality of the material of the rotor apex seal. I don't know, maybe this. Yeah, I would say that for sure, like there's a, if this is the question, the advancement in metallurgic technology made a lot of improvement in terms of apex seals. Indeed, like in Wankel rotor engine, now they are employing ceramic seals, so they overcome all the drawbacks that they had in the past. That's why this kind of engine are coming back. Mazda proposed a new range extender running on Wankel engine just this year. So they are not really, it's a big company. They are not crazy to kill themselves, to shoot themselves in the foot if they are proposing. They have the right technology for sure. That means like the Wankel engine is something that is feasible. The things that the engine that I was showing before is a small engine, 225, but from the performance that we were evaluating is able to do 29% of efficiency without any optimization in terms of ECU strategy. It was an engine applied to small drones that they are not subject to any emission or any fuel consumption regulation. That the engine was not really optimized. So that made us believe that the engine can be optimized and can reach even higher performance in terms of efficiency, 32 or 33%. That is not really bad for a small engine like that one. The other question was like the energy density is affecting the application. Yes, of course, for the engine, of course, the engine, internal combustion engine are just relying on energy density. Of course, as Jamie was saying before, for hydrogen is a bit of a problem because storing the hydrogen is really high in terms of energy, but storing it in order to have the right density stored it's a kind of a problem, as Jamie was saying before, because you have to compress it up to 700 bar. That makes it like the real problem of hydrogen application. We are not really concerned by the engine itself, but the storage is really a problem. If that was the answer, if the question.
So thank you very much. I think in the interest of time, we are a bit late. We need to move on. So thank you very much for the talk.
Thanks so much for having me. My pleasure.